All right. The new thing for today, we are going to take what we did last time with calorimetry, and we are going to combine it with what we did with stoichiometry. We're going to put those two skills together and do what we know as thermochemistry. Now today we're just going to work on the stoichiometry part of it, and then next week we'll put the stoichiometry with the calorimetry, and the whole thing comes together. All right, so calorimetry, just a quick reminder. This is the study of heat transfer. What you're going to see today is that it is the study of how much heat we actually get, heat energy out of a given reaction. Heat is energy, and so just like we generate products that are physical, things such as liquids, gases, and solids, we can also generate energy. Energy can be transferred. It is stored in the chemical bonds, so when we break the bonds, we release the energy. And if you're thinking, okay, if we make bonds, does that mean we put energy in? Yes. So if we are breaking bonds, we are releasing energy. All right. So remember that we calculated heat energy with that lower case Q. And we're going to use Q in our stoichiometry. All right, so the process of thermochemistry. It's the same as stoichiometry. Everything that you've been doing, keep doing it. If you've been good at it, you're going to be great at stoichiometry. If you're not quite there yet, this is more practice and you'll be great. All right, we add heat energy to our recipe, to our standard reaction. And heat energy in the recipe is delta H. And that's just, it's an old school chemistry thing, and you're rarely going to see that other than where I use the number. And I will point that out to you. Where do they come from? We can calculate them in a laboratory or look them up on the internet. All right, and then the letter Q. Letter Q is how much we actually are going to get, how much heat energy out of a given equation. All right, so let's see how this actually works. We're going to make some water. Synthesis reaction, right? Hydrogen plus oxygen makes water. And in doing that, we actually generate 286 kilojoules, that's 1,000 joules, 286,000 joules of energy. That's how much we get out when we make water, by taking hydrogen and oxygen and putting them together. All right, so if we put this into a stoichiometry problem, let's see what we actually are able to get. All right, so I'm going to switch over to Apple TV here so that we can actually, there we go, one more time. All right, there we are. All right, so the stoichiometry looks just like you're used to doing. Step one, write the reactants. There they are, hydrogen plus oxygen. Write the product. H, because it's furthest to the left, and O. There it is. Check for diatomics. Step 3. Well, we know that hydrogen and oxygen are both diatomic. Step 4. Need to balance our molecules. Hydrogen's +1, oxygen -2. Switch the numbers. All right, and you knew that before we started. We get H2O. All right, there we are. We'll put those up front because we have to balance this. So balancing the reaction looks like this. Okay, 2, 1, and 2. All right, now we're going to set up the problem just the way that you always have. 2 lines underneath, 1 line above. Remember, this is moles. Grams down here. I'm not going to write given because I need that space for something else this time. All right, so we've got our problem pretty well set up, except for one thing, the heat energy. Well, I said that this reaction generates 286,000 joules of energy, so we're just going to tag that right out here, plus 286 kilojoules. That's how much energy is generated. So we just added it onto the back end, and up here right above it, we're going to put another space. It's kilojoules, not moles though. And guess what? This is Q. The magic Q, there it is. All right, so let's go ahead and get going here. We are going to, I think, we're going to start up, let's do 12 grams of hydrogen, let's do 64 grams of oxygen. We've got to get how much each of these are. Let's see, so this is 1 plus 1 equals, so that's 2 grams. This is 16 plus 16 for 32. That's the atomic weights. This is 1 plus 1 plus 16. So that is 18 grams. That's what we're given. All right, we're going to do some division. Remember, don't flip this upside down. Do it just the way it is. 12 divided by 2 is 6. Put those numbers right up there. Doing this just the way we always have. 64 divided by 32 is 2. All right, now we have to do a little bit of division up on the top here. Remember, we're going to look at these two and decide which one is less. So 6 divided by 2 is 3. 2 divided by 1 is 2. That one's the smaller one. That's the one we're going to use as we move forward. So we're going to use that right here. 2 divided by 1 equals, remember this is x right there. So we got to do this one right here. So 2 over 1 is x over 2. All right? And so, yeah, that's it, 4. Okay? The last one. We're going to do this. I'm going to change colors for a moment because we are going to do this one the same as we did the others. We're going to take this same limiting one, oops, I moved that back, this same limiting one of 2 over 1, only this time it's going to be equal, if we get that to work there, it's going to be equal to Q over 286. All right? So we just have to do a little bit of math there. 2 times 286, 2 times 286 is 572. All right? Okay, we are almost done. This is all done right there. That's how much energy comes out of it, 572,000 kilojoules. We just have one more thing to do here. We don't want to forget calculating our product. 4 moles times 18, 4 times 18 is 72 grams. So we end up with 72 grams, okay, of water and 572,000 kilojoules of energy. And that's how we do the first thermochemistry problem.